Yeah, good afternoon, everyone. I am Jeong from Baylor University, and my advisor is Professor J.B. Lee. It is a great honor for me to present my research work in the Sensors Conference. So I will first go with the background of my research. So tilt sensors are used in various areas like robotics, automobiles, and aerospace to measure tilt angles. So one of the key parts in the tilt sensor is the pendulum, so which can be made from different materials such as the solid, liquid, or gas. So among these pendulum, liquid-based tilt sensors stand out because it offers high resolution, has simple design, and a high resistance to collision and moisture, so compared to other tilt sensors using the solid or gas pendulum. So there are several ways to measure the angle in liquid-based tilt sensor, like capacitive, magnetic, electrolytic, and resistive method. So when it comes to tilt sensor using liquid pendulum, sensitivity is one of the most important figure of merit. So from the formula, high sensitivity means a higher response of sensing element in terms of capacitance, frequency, voltage, or resistance after tilting. And however, sensitivity in liquid-based tilt sensor is limited by the area variation of the sensing element in liquid pendulum. So here are the sensitivity for different tilt sensors. So let me slightly change the topic in this slide. So gallium-based liquid metal alloy like gallium or EGain is a metal in a liquid state at room temperature. So it has superior electrical conductivity, excellent fluidity, and is biocompatible unlike mercury. So we thought that liquid metal is ideal to be used in variable register as liquid wiper. However, gallium-based liquid metal forms a thin layer of gallium oxide skin in ambient air. This oxide skin sticks to almost any surface. Such a sticky nature of liquid metal has been often considered as a significant problem in various applications. So in 2014, laser-induced graphene, or LIG, using a commercial polyimide and CO2 infrared laser was reported. LIG can be easily made from polymers and has non-wetting characteristic for gallium-based liquid metals. Additionally, it has high resistivity, making it a promising candidate as a resistive element in variable register. So combining these two materials, gallium-based liquid metal and LIG, Babatian et al. Developed a resistive liquid metal inertial sensor based on a principle of variable register. So when the liquid metal droplet moves between the two LIG lines, by tilting, it makes the resistance changes. Based on the resistance formula, with liquid metal droplet movement, the overall length of LIG can be increased or decreased, thus very high resistance variation can be achieved. So our approach in a lace track shape, a dense array of serpentine LIG electrode can be used as the ultra-high resistive element for the tilt sensor. So when the sensor is tilted, LIG electrode emerges from the liquid metal base, creating a resistive circuit between cathode and anode. So here one of the important things is having higher length of the resistive circuit. We envisioned a resistive serpentine LIG electrode with liquid metal pendulum as tilt sensor. So through this mechanism, the tilt sensor can achieve ultra-high sensitivity if the length of a resistive circuit becomes remarkably long by tilting. So let me talk about how the tilt sensor is fabricated and experimental research. So we use the 3D printed substrate to make a chamber. So Kapton tape was attached to the 3D printed substrate as a precursor for LIG fabrication. Permanent magnets were used with each substrate to keep the chamber intact. Then diode laser is used to fabricate the LIG wire and LIG connector on Kapton-coated substrate. Next, the serpentine LIG electrode was fabricated on Kapton-coated substrate. Then copper tapes were attached to LIG connectors as cathode and anode. And for substrate with LIG electrode, LIG connector, and LIG wire were attached to the 3D printed chamber using permanent magnets. Finally, gallium stain was injected into 3D printed chamber by a syringe. So we studied various laser parameters to find an optimal processing condition for maximum sensitivity. The optical images show 10 mm LIG lines under various processing conditions of the laser. We measured the resistance of LIG line with different width and height by changing the power and velocity for the laser. It was found that the resistance increases with increased velocity and it decreases with increased power. We selected the power of 1.8 watt and speed of 5 mm per second, showing highest resistance of LIG line, and these parameters were used to fabricate the dense array serpentine LIG electrode. Design of LIG electrode is shown in this slide. To make our surfaces non-wetting to gallium-based liquid metal, LIG wire is made. We fabricated LIG connector to connect LIG electrode with cathode or anode. Length of each LIG electrode line is 10 mm, and the angle between each LIG line was designed to be 1 degree. We found that gaps larger than 200 micrometer made the surface wettable to oxidize gallium-based liquid metal. Under the gap size of 200 micrometer, there is a high risk of electrical shortage, so the gap between LIG wire and LIG electrode was designed to be 200 micrometer. The optical images for LIG electrode, wire, and connector are shown in the right side. Here are the optical images of the tilt sensor and the tested surface when the sensor was tilted between. The sensor was tested by tilting 100 times in clockwise and counterclockwise direction from minus 45 degrees and 45 degrees. And from the close-up images for LIG electrode, it is quite apparent that there was no sign of surface wetting by liquid metal on the sample. The graph shows resistance as a function of the tilt angle from minus 45 degrees to 45 degrees. This graph shows us the linearity between resistance and tilt angles. Here, the resistance of tilt sensor at 0 degree is 1.2 ohm, and 45 degrees, it is measured as 404.4 kilo ohm. The tilt sensor shows ultra-high sensitivity of 8.9 kilo ohm per degrees compared to conventional liquid metal tilt sensor. So in conclusions, the tilt sensor was fabricated using laser-induced graphene LIG register and liquid metal pendulum. LIG line was optimized by changing the laser condition to increase the sensitivity of the tilt sensor. Aided by the serpentine LIG electrode, the proposed tilt sensor can achieve ultra-high sensitivity of 8.9 kilo ohm per degree, which is several orders of magnitude higher than previous work. So here I would like to thank the National Science Foundation for their grant support and thank my lab colleague for their help. Thank you for your attention. If you have any question, I will be more than happy to answer your question. Thank you so much.